Here we just want to work through another power series example to show you some other things that can come up and how to handle them. So let's find the first three non-zero terms in each part of the two linearly independent power series solutions about x equals 1 for the differential equation y double prime minus x times y equals 0. Now notice that since the function p of x, which is 0 here, and q of x, which is negative x here, they're both analytic at x equals 1. Therefore, x equals 1 is an ordinary point, and we have the green light to apply our previous techniques. So we will look for a power series solution about x equals 1. So this is a difference from our last example. And so we start with this template. And if you want to write it out in its expanded form, you get this. We will, in preparation for substituting this into our differential equation, we will take the first derivative term by term. Remember, when you take the derivative, you're going to lose a constant term from your y. So now your index, this is very important, needs to start at 1 now instead of at 0 because you're going to lose this a0 term. When you take another derivative, you're going to lose this constant term. So you take the derivative term by term, but you need to remember to shift your index, and it starts now at 2 instead of 1. So here's the summation form for each, and here's the expanded form for each. Now we want to substitute these back into the differential equation, which is y double prime minus x times y equals 0. We substitute in y double prime minus x times y equals 0. And if you stare at this for a second, in the past what we would have done was try to shift the index to get the x power terms to match on the back end, and then we would have peeled off terms from the summation to get the starting index to match. But we can't even get started with that because notice here we have x minus 1 to the n, and here we have an x, and we can't just distribute this inside and combine it with this. So this is in contrast to our previous examples. We really need this to be an x minus 1, not an x, so that it can be combined with this term. Now we can't just change this to an x minus 1, but we can back up a step, go back to our differential equation, and say, well, if we really want there to be an x minus 1 here, then having an x minus 1 there would have given us a y double prime minus parentheses x minus 1 times y, and that's not the same as we have here. We're off by an extra y term. Notice a minus y has now appeared here, but we can offset that by subtracting off a y term because this is really contributing a positive y. We'll offset that by putting a minus y in here, and now this differential equation is algebraically equivalent to this differential equation. But this differential equation has the upside that when we write it in its series form, y double prime minus x minus 1 times y minus a y, that now we have an x minus 1 coefficient that plays nicely with this x minus 1 to the n that's inside the series, and now we can proceed as before. So this is definitely something you want to keep in mind when these are not algebraically compatible, how you can usually make some kind of manipulation like this to force them to be compatible. Of course, you can't just change this. You have to offset it by whatever is necessary to get the type of structure that you need to proceed. Well, now this feels like one of our familiar problems, and so we look and we say, well, at the back end we want an x minus 1 to the n, and we have that on these two. On this one I don't, so I need to shift the index. And also, before I do that, I need to take this x minus 1 to the first power, and I need to put this in here. So they match right now, but I still have to multiply by this. So let's do that first. When I do that, I get this, bumps the power up by 1. And now I look at the x minus 1 powers on the back end. This is an n plus 1. This is an n minus 2. Why don't we make them all, it doesn't matter what we make them all be as long as we make them the same thing. Why don't we make them all be an nth power? So this is fine. We need to shift this index down 1, up 1. We need to shift this down 2, so down 2, down 2, down 2, down 2, up 2. When we do that, this stays the same. Here we shifted this down 1, up 1. This was up 2, up 2, up 2, up 2, Now the index went here down 2. And now we have gotten what we want in terms of they all match on the back end with an x minus 1 to the n. So now we need to peel off whatever the appropriate terms are. Notice this one starts at n equals 0, n equals 1, n equals 0. The latest one is really dictating things. This starts the latest. So that means we need to peel off the n equals 0 term from here, and we need to peel off the n equals 0 term from here. Okay, to do that, for this series, when n is 0, we get a2 times 1 times x minus 1 to the 0. So that's just a2 times 2 times 1. Plus, we have all the other terms that start from 1 and go to infinity. So we peeled off the n equals 0 term here. Don't forget all the other terms. Here, we are going to leave this alone. Here, we need to peel off the n equals 0 term, which would be a0 times x minus 1 to the 0. So that's just an a0. It does have a minus in front of it. So we have a minus a0 minus all the other terms. Now they start from 1 and go to infinity. And this equals 0 because that was the right-hand side of our differential equation. Okay, so now if you stare at the part that have sums in them, they all have a common x minus 1 to the n on the back end, and they all start at n equals 1. So that means we can write them as one big summation. And the things that do not have a sum on them, we will gather them together. And we will group our like terms when doing so. So this just gives me, when we gather these terms together, we get a 2a2 minus an a0, we'll keep that together, plus one big summation, and then what's inside the sum is an an plus 2 times n plus 2 times n plus 1 minus an an minus 1 minus an an. So that's what we see in the brackets here, all times x minus 1 to the n. Now, just as we argued before, this is just an infinitely long polynomial, if you will, and it equals 0. So the only way that this can equal 0 is if each corresponding coefficient that's playing the role of the coefficient in the polynomial is 0. So notice if we group these together, this is our constant term in our polynomial, not individually, but together. Together, this term must be a 0. And then since the quantity in the brackets is the coefficient for the nth term, the nth power term here, this must equal 0 in the brackets in order to get the entire polynomial, infinitely long polynomial, to be 0. So if this is 0, this gives me this. If this is 0, we'll just first set it equal to 0, realizing that this is true when n equals 1, 2, 3, dot, dot, dot. And now if we solve for the future in terms of the past, we get an plus 2 is an plus an minus 1 all over n plus 2 times n plus 1. And this is our recurrence relation. This is a little different than our last example. This is called a two-term recurrence relation because when we solve for the future in terms of the past, now we have two terms instead of before we only had one term. We had a one-term recurrence relation. And you can get recurrence relations to where it depends. Here, notice it depends on two of the terms that happened before the current term. So we're still going to proceed as we always have. Well, this is the seed for our recursion. We're just going to say, well, this starts when n is 1. That's why it's very important to have an accurate index here. This starts at when n is 1. So we'll substitute when n is 1. We'll substitute that back into this. And we get a3 equals a1 plus a0 over 2 times 1, 3 times 2. And when we look at this, we could rewrite this as an a1 over 6 plus an a0 over 6, as we have here. And notice that we don't know anything about a0 or a1, so we just stop. Okay? Now if we do, we substitute n equals 2 into this, we get a4 is a2 plus a1 all over 4 times 3. Notice we can rewrite this as 1/12 a2 plus 1/12 a1. Now we do know something about a2. a2 is 1/2 a0. So when we come here, where we see an a2, we'll put a 1/2 a0. We'll simplify this. We still don't know anything about a1, so we leave this alone. And this is the best that we can do. Let's do another one. When n is 3, we get a5 equals a3 plus a2 all over 5 times 4. So again, this is a 1/20th a3 but I know what A3 is. A3 is this. So first let's write it out. This is a 1/20th A3 plus a 1/20th A2. Now we look back and we say, well, I know what A3 is. A3 is this. So I'll substitute that in for A3. But I also know what A2 is. So I'll substitute that in for A2. I will simplify this. And when the algebra dust settles, we get a 1 over 120 A1 plus 1 over 30 A0. And we could keep doing this all day and generate as many coefficients as you like. So let's go back to generate our solution. And this is where, in practice, when the instructions say write out the first 3 non-zero terms in each part of the 2 linearly independent power series solutions, I'm going to show you how you know when you've gone far enough. Okay? So if we go back to our power series, this was our template. Y of x was the sum from n equals 0 to infinity of a sub n times x minus 1 to the n. I'm just going to write this out in its expanded form just to help us get a feel for it. Keep in mind, I don't know anything about A0. I don't know anything about A1. But I do know what A2 is in terms of A0. And then I know A3 in terms of A0 and A1. I know A4 in terms of A0 and A1. I know A5 in terms of A0 and A1. So I'm going to leverage these things next. So we were here. So now we don't know about A0. We don't know about A1. We know A2 is 1/2 A0. We'll substitute that in. Don't forget, it's the coefficient. A2 is the coefficient of the x minus 1 quantity squared term. But A2 is this. A3 was this. A4 was this. Don't forget your powers. Your x minus a to the power n, whatever your a and your n are. So don't forget this. It's very common for students to forget this. Plus, this would be what we get for the coefficient of x minus 1 to the 5th. And then it goes on forever. Very important that you don't leave this off either, because you're recognizing the fact that this really is an infinite series and not a finite sum. And now if you stare at this for just a minute, notice that every term in here either has an A0 or an A1 involved in it. So why don't we just separate out all the terms that have A0, so this, 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 separate all those out and segregate them and factor out the A0. If you do that, you'll get an A0 times this infinite sum plus, look at the terms that are left over that have A1s in them. So you have this, you'll have this, you'll have this, and you'll have this. And it goes on forever. And if you group those together and factor out the A1, you'll get this. Now, if you notice, this first quantity in brackets is itself an infinite series, a power series. And the second quantity in the brackets is a different infinite power series here. So notice what we've got. We've got an A0 times this function defined in terms of a power series. Think of it as being a y1 of x, plus an A1 times this function, which is defined in terms of a power series. Think of it as being a y2. So what we've just found is a 2-parameter family of solutions for this second order differential equation. That's exactly what our theory says should happen. We just didn't get a closed form for y1 and y2. Instead, we got this infinite power series form. And that's totally fine, totally acceptable, and can happen. And so this is what it meant when it said find the first, at least the first 3 non-zero terms in each of the 2 linearly independent power series solutions that makes up the general solution. Now, I have not proven the linear independence part. We could do that using Wronskians, but these are linearly independent. And we found much more than was asked for, because notice here we found the first 1, 2, 3, 4, 5 terms in each. 1, 2, 3, 4. Well, we found the first 5 here. We found the first 4 here. We've certainly satisfied what they've asked us to do. So a couple of new things going on in this example. One is that if you hit sort of this algebra roadblock to where the coefficient function doesn't play nicely with the center of your series, and so you can't just straightforwardly combine and bump the powers up, you could usually pull an algebraic stunt like this to get you out of that. Then it becomes something very similar to what we've done before, exactly like what we've done before. But in this example, we got a two-term recurrence relation. It didn't really make any difference to us. We proceeded just like we did before. The difference in these two-term recurrence relations is, notice how we have two terms here. We were able to get all of our future coefficients back in terms of just the first two coefficients, a0 and a1. And that feels right since it is a second order equation. We expect to get a two-parameter family of solutions. We expect there to be two constants in the solution that we're not able to get our hands on. And so this is how that plays out here. And then don't forget, when we put it all together, we're going to go back to the template for our solution. We could work with it in summation form, or we can expand it out. I think expanding it out really helps you see things. We're going to expand it out. We're going to substitute in what we know about our coefficients. And what should happen is, since you should only have two constants in your solution, everything here should be in terms of a0 and a1. And then we explicitly group the a0 parts separately from the a1 parts. And this gives us an a0 y1 plus an a1 times a y2. And so we do get two linearly independent power series solutions that are forming our general solution.